So, Chapter 1, we're going to take a look at quantities and units. In quantities and units, we've got 5 sections: units of measure, scientific notation, engineering notation and metric prefixes, metric unit conversions, and measured numbers. So all of these values and all of these conversions and units you should have already seen if you took ET131B, the math for electronics, and you should have some proficiency in doing these already. If you haven't taken the course or you need a review, I posted a link to YouTubes that I created for my Math 111 class, and that might help you to move forward and do a review if you need to. So the chapter objectives, we're going to discuss the SI standard, the use of scientific notation, powers of 10 to express quantities, the use of engineering notation and metric prefixes to represent large and small quantities, convert from one unit with a metric prefix to another, and express measured data with proper numbers of significant digits. So this is all important. This is all mathematical relationships and manipulations that you absolutely need to be familiar with by now in this course in ET131. You should be used to using your powers of 10 and your scientific and engineering notation instead of writing out numbers with lots of zeros on them. Do not do that. Use the exponents, use your metric and scientific notation to express your answers. The key terms then, all of these are terms that you need to be intimately familiar with. If you're not dreaming in the terms of these values and these expressions, you're not trying hard enough. So you need to be dreaming about these things like scientific notation, powers of 10, exponents, engineering notation, metric prefixes, significant digits. In looking at the different quantities associated with the values in terms of fundamental values and derived values, the thing to keep in mind is that a fundamental value usually only has one measure. In this case, length is in meters, and we use the symbol m. So it is not a multiple value. It's not an exponential value. It's length, it's meters, the symbol is m. The same thing with mass, kilograms, time, seconds. Electric current, amps, temperature, Kelvin, luminous intensity, candela, if we use that value, amounts of a subject, a mole. You know, these last two values you're not going to use as much in a course like this, but it's good to be familiar with them in case you see them in any other value or description. In terms of angles, as we move on in this course, you will be getting into the use of angles, and you will use degrees and radians. The quantity for an angle in a plane is a radian. That one we will be using a lot as we move along and get into the alternating current measures. The solid angle, though, that they introduce in your text, the steradian, not something you're going to use. You can see in the diagram below what the steradian actually amounts to, and this is actually a volumetric relationship. So it's not something you're going to see and or use in this course, or particularly in a degree program like this. Looking at fundamental units for things like capacitance, charge, conductance, energy, frequency, impedance, inductance, power, reactance, resistance, and voltage. Again, we use the corresponding symbols for them when we write them out mathematically. We also use the SI unit. So a capacitance, symbol C, we use the SI unit of a farad, and we use the capital S. Conductance, we use G, and we call it in Siemens, or S. We don't typically use the term mho anymore, which is ohms spelled backwards. Okay, impedance, Z is the term we're going to use. We're going to get used to using the term Z for impedance versus R for resistance, because we're going to find out that Z is made up of a real and an imaginary part, and we're going to get to that later. So instead of writing out ohms, we're going to use the symbol for ohms. Okay, you'll notice here on the bottom, reactance and resistance, real and imaginary resistance values, X and R, both of them use the symbol ohm. When we get to magnetics and electromagnetics, magnetic field intensity, H, amperes per turn. So now we have a derived unit. You'll notice that we have an amount of current based on the number of turns of wire divided by a length in meters. So we have ampere turns per meter. Magnetic flux, we use the little symbol phi, Weber, WB. Magnetic flux density, we use the capital B. The SI unit is the Tesla, or T, which can be a little confusing because we also use T for units like tera. Magnetomotive force, F sub m, get used to using that relationship, value sub some unit of measure. F sub m is an ampere turn. So this is basically what we saw in the numerator up here for magnetic field intensity. A little more complex one, the permeability, we use the Greek letter mu, which is Webers per ampere turn per meter. So we've taken the magnetic flux intensity, we've stuffed it into the denominator, and we're dividing it into the magnetic flux, or Weber. The last one, reluctance, the stylized R, ampere turns per Weber. Now we've combined these terms. So we've taken fundamental values, fundamental units, and created units from them that we call the derived units. Okay, so when we come back, now we're going to start looking at dealing with values in terms of scientific notation.